Swayam Prabha. Digital India. Educated India.
Welcome back to the course Geology and Soil Mechanics. So, today we are going to start the new topic, that is shear strength of soil. So, this is very important to understand the stability or the failure happening in the soil. Now, any geotechnical structure, if you think of like your earth returning structure or your soil embankment, soil slope, and then foundations, and any kind of say geotechnical structure if you consider. So, basically to find out the ultimate limit or ultimate strength of those structure, that means the till the failure how much it takes care of the load. So, if you want to find out that, say for example, you might have seen this is quite common phenomena in the natural life, that landslide, right. So, you might have seen or you might have heard this phenomena, that landslide. So, landslide is basically is caused by the instability happening in the soil. Now, what kind of instability and how this instability is happening? So, any material if you consider in the world, every material will be having some limit, okay, to carry any kind of load, right. So, if I give you or if I ask you to carry some 10 kg of load, you can carry, right. If I ask you 20 kg of load, still you can carry. But if I ask you 100 kg of load, you cannot carry. So, you have some inherent limit. So, that limit is nothing but the strength, right. You have some inherent strength by which you can carry different kinds or different amounts of load, right. The same thing is applicable to the soil also. So, soil is having some inherent strength, and that strength is nothing but your shear strength. We will see that this strength is basically associated with the shear resistance or the shear force happening in the soil at a particular surface or particular plane. Now, this resistance or this shear strength basically will try to resist whatever load is coming on top of the soil or whatever external forces are coming on top of the soil. Suppose for example, the foundation, if you consider the building foundation. So, the foundation will be having some limit, because the soil will be having some limit. So, each foundation will be having some limit to carry the load. So, you cannot go on extending the load on a particular type of foundation, right. You cannot, if your foundation can carry say 10 ton per meter square load, you cannot apply or you cannot impose some say 25 ton per meter square load on top of the foundation. So, your foundation will be undergoing failure, right. Similarly, in case of your slope stability or the returning structure or the even landslide, right. So, every soil will be having some resistance along any particular surface, right. So, and if some instability is happening, if that limit is reaching at that particular surface, the soil will try to flow or try to slide over the surface, and that is why the landslide happens, right, due to some instability. Now, basically the shear strength of a soil mass is the internal resistance per unit area that the soil mass can offer to resist failure and sliding along any plane inside it. So, for example, say you have some embankment kind of thing, okay, or you have some slope, natural slope. Okay. Now, the soil, you might have seen the soil that landslide or the soil failure, it is happening like that, right. So, this part of soil, this shaded part of soil, it will try to move in this direction, flow in this direction, right. Now, why? So, this, if you consider this surface, if you consider this curved surface, right. So, along that surface some instability is happening, that is why the shaded soil part is getting detached or getting separated out from the rest of the soil body, right. So, this surface is becoming some critical surface, and that is known as the failure surface, and along that failure surface your resistance, right. So, soil is, if you apply some load, and that I mean due to that load basically the internal resistance will be getting developed, right. So, if I ask you to carry some load, so your internal muscle or internal say strength will be coming out, and that will try to resist that much of load, external load. Similar kind of thing is happening in soil also. So, when this weight of the soil is causing, that shaded part of the soil is causing some extra load, or it is crossing the limit of the soil resistance, then it will try to move in this direction or the move along this plane. So, that is why it is known as the internal resistance, that is the internal or inherent property of the soil, internal resistance per unit area that the soil mass can offer to resist failure. So, when this wedge will try to flow in this direction, so your resistance will be acting in the opposite direction, right. So, the action, so if this is the direction of action, your direction of reaction or the resistance will be just in the opposite direction, right. So, I mean it will try to resist the failure on and sliding along any plane. So, along any plane, as I showed you, this is the plane, along this plane basically it will try to resist the sliding. Now, I mean unless till you are within the limit of the soil strength, basically this sliding or this failure will not be happening. Once you cross or once you reach, that means on the verge of failure, basically what will happen, the wedge will try to flow or try to slide over the surface, right, and that is why you get the landslide or the slope failure or the retaining structure failure, some kind, that kind of thing, right. So, basically it tells you that if you have the instability, so gradually you are applying load, and gradually your strength is getting mobilized along that surface, and once it reaches the strength limit, right, it will collapse or it will fail, right. So, now we are going to analyze, I hope that you have understood what is the phenomena of shear strength. So, now we are going to analyze this shear strength, and we will like to establish the relations or the failure criteria for this kind of shear failure, and also we will see that what are the different types of laboratory experiments available to determine the shear strength of soil, as well as some field experiment by which you can determine the shear strength of soil. So, those things we will see in this particular chapter. So, first we should understand the Mohr-Coulomb failure criteria. I hope that you are quite familiar to the different failure criteria from your mechanics course, like von Mises failure criteria, Tresca failure criteria, Drucker-Prager failure criteria, similarly Mohr-Coulomb failure criteria. So, what is the Mohr-Coulomb failure criteria? Let us talk about that, and once we establish the Mohr-Coulomb failure criteria, and based on that we will try to establish the relation of shear strength and shear stress. Now, Mohr in 1900 presented a theory for rupture in materials that contended that a material fails because of a critical combination of normal and shear stress, and not from either maximum normal or shear stress alone, right. So, what it says, that any material will undergo some failure when some critical combination of normal and shear stress is happening. Critical combination means it is not I cannot get the failure if the normal stress is getting maximum or the shear stress is getting maximum. So, this is the common common thinking, right. So, if my normal stress is getting maximum, then I may get the failure. No, Mohr is saying no, you may not get the failure at the maximum normal stress, or you may not get the failure at the maximum shear stress. When the maximum shear stress is happening, that means you are applying some external load on top of the soil, and due to that you are getting some shear stress developed in the soil, as well as normal stress developed in the soil, and those shear stress and normal stress, when they are reaching maximum, that may not be the point where you will be getting the failure. Rather, you will be getting the failure at a critical combination of shear and normal stress, right. So, either maximum normal stress or maximum shear stress will not cause the failure, rather you will be getting some combination, critical combination of normal and shear stress, where you will be getting or where the failure will be initiated in the soil or the material, right. So, basically that is expressed in mathematically, that is expressed tau f, that is a shear strength, is equal to function of normal and shear stress, right. So, this is the function, and we will try to establish this function now. Now, the failure envelope, right. So, if this equation 5.1 is giving me the failure envelope means that is the limit, or that is the surface, okay, on which the failure occurs, right. If you draw in case of 2D situation, you will be getting in case of 1D situation, you will be getting one point, right, in stress strain in stress strain say space. In case of 2D, you will be getting one plane, okay, along which once the combination of your loading is reaching that or touching that plane, immediately you will be getting the failure, that is known as failure plane. In case of 3D, you will be getting the surface, right. So, along the surface, suppose this is my surface, this is creating the limit. So, if I am within this limit, there is no failure, failure is not happening there, but at some critical combination of shear and normal stress, I am just touching this surface, or in 2D it is plane. So, if I touch the plane, immediately I will get the failure. So, that it says. So, the failure envelope defined by equation 5.1 is a curved line. Frankly speaking, this is a curved line, this is a nonlinear failure envelope. However, for most soil mechanics problem, it is sufficient to approximate the shear stress on the failure plane as a linear function of the normal stress. Okay. In most of the soil mechanics problem, we generally consider that it is a linear function. This failure envelope, whatever you have got from equation 5.1. So, that was giving me the curved failure envelope, right. But Coulomb in 1776, I mean, he proposed that basically you can consider this function as a linear function, okay, and it will not cause any difficulty or cause any problem to understand or to predict the behavior of soil. Okay. So, this nonlinear failure envelope. So, earlier you are getting this kind of a failure envelope. So, suppose for example, now you are approximating this failure envelope as nonlinear, linear, okay, as per Coulomb's. Okay. So, this nonlinear failure envelope is becoming linear failure envelope by choosing the Coulomb's failure criteria. So, now basically this linear function or this linear failure envelope can be expressed by this expression tau f is equal to C plus sigma tan phi, where C is the cohesion, C is known as the cohesion, okay, in the soil. So, suppose this is grain to grain say cohesion, okay. Tau f is the shear strength, that is the limit or the strength of the soil, that is the inherent limit or inherent strength, and sigma is the normal stress on the failure plane. Okay. So, suppose if you have some failure plane and if you want to find out the shear strength along that failure plane, because when I am talking about the failure, then only you will be talking about the shear strength. Otherwise, any surface, any plane you consider, along that plane some shear stress is acting, but that shear stress when it will reach the maximum limit, at that time failure will be happening, and that plane will be identified as the failure plane, and along that plane whatever shear stress is acting, that is nothing but the shear strength, that is the maximum limit of the soil. Okay. So, if I consider this is my failure plane along which whatever say normal stress is acting, say sigma, okay, and if I know the phi, where is phi is nothing but angle of internal friction. So, soil will be showing two different kinds of. So, basically the shear resistance will be dissipated through cohesion and through friction. Okay. So, this phi is nothing but the angle of internal friction. If you recall your 10+2 standard friction chapter. So, basically if that is nothing but the friction angle. Okay. This phi is nothing but the friction angle. So, if I consider sigma is acting on this plane, that is nothing but the normal stress, and if I want to find out the shear strength tau f, that tau f can be obtained by this expression, where tau f is equal to C plus sigma tan phi. Okay. Now, we can, the preceding equation is called the Mohr-Coulomb failure criteria. Okay, whatever equation we have seen in equation 5.2, that is basically known as Mohr-Coulomb failure criteria. Okay. Now, if you try to obtain the Mohr-Coulomb failure criterion expressed in terms of effective stress, of course, tau f will be equal to C prime, that is the effective cohesion, plus sigma prime, that is the effective normal stress, into tan phi, whereas phi is the effective angle of internal friction. Okay. I mean, everything is expressed in terms of effective parameter. Now, the value of C prime, that is the effective cohesion for sand and inorganic clay, is 0. And this is quite obvious. If you take some dry sand or the inorganic silt, you will see that the cohesion between the particle, okay, is negligible or simply 0. So, if you think of cohesion value is 0 for sand and inorganic silt, so that is quite good, that is quite logical, and that you can get it from the test also, laboratory experiment. So, for normally consolidated clay, C prime is, that is the effective cohesion, is found to be 0. However, for over consolidated clay, C prime is greater than 0. Okay. So, these things generally happens, okay, in soil mechanics. Now, this is your Mohr-Coulomb failure criteria. So, you are plotting the line between shear stress and normal stress. Okay. So, effective normal stress versus shear stress. Okay. Now, basically if you look at this plot, what you are getting? You are getting some linear failure envelope. So, this is your linear failure envelope, Mohr-Coulomb failure criteria, that is given as tau f is equal to C prime plus sigma prime tan phi prime. So, where phi prime is the angle of inclination of this line and C prime is the intercept on the shear stress axis. So, now basically you are getting, so this the equation of this line will give you the Mohr-Coulomb failure criteria, that is nothing but, so if you touch this line, basically you are getting the failure. So, if you are on this line, you are getting the failure. So, tau f, that is the y axis, is equal to C prime plus sigma prime tan phi prime. Okay. So, this is basically the equation of this straight line, and that is nothing but your Mohr-Coulomb failure criteria. Now, if you look at this figure, okay, so now you have understood one thing, you will be getting some critical combination of sigma and tau, right, shear stress and normal stress, for which you are getting the failure. You are not getting the failure either at maximum normal stress or at maximum shear stress, rather you are getting some critical combination of sigma prime and tau, so that you are getting the failure along this line. Now, you are choosing 3 different points, say point A, point B and point C. For example, you are choosing 3 different points at different locations in this plot. Point A is below the failure envelope means this straight line. Point B is lying on the failure envelope and point C is lying above the failure envelope. And let's try to opine on these points. I mean, whether this, what type of points and what these points are really mean for. So, those things we are going to look at. Okay. Now, point A, at point A, shear failure will not occur, agreed. So, any combination of sigma and tau, whatever combination you choose, if that combination is lying below the failure envelope, like point A, you can get another point here, you can get another point here, you can get another point, you can get n number of points which are lying below the failure envelope, failure will not occur for that combination of sigma and tau, agreed. Now, at point B, shear failure will occur. What is point B? Point B is exactly relying on the failure envelope. So, any point which is touching or which is lying on this failure envelope, that for that combination of sigma and tau you will be getting the failure, right. Now, what about point C? At point C, a state of stress does not exist, because I mean you can move from any point to any point by varying the sigma and tau, and ultimately this is your boundary, this is your limit, that is the limiting condition. The soil is saying beyond this limit I cannot take the load. So, you cannot have the access beyond this line. So, you can roam around whatever points are here in this zone, right. So, and maximum you can go up to this line. So, this is the maximum limit. Beyond that limit, whatever point C is lying or whatever point are lying here in this zone, basically you cannot have the access, you cannot go inside those region, right. So, basically the region which is defined by this strength or by this failure envelope, right. So, within that region you can roam around and you can get different combination of shear strength and normal stress, and for that you can say whether the failure is happening or the failure is not happening. You cannot go beyond the failure. Now, basically we will look at this, say a Moore Coulomb failure criteria in different way, not different way, same way, but for different say combinations or say different concepts we are going to find out from this plot. Now, what we are considering? We are considering one soil element like this. So, A, B, C, D is my soil element, say along AB plane and along CD plane the sigma 1, that is the major principal stress is acting, everything is expressed in terms of effective stress. So, I am putting prime. So, whenever I am putting prime, so prime will indicate those parameters are effective parameters. Okay. So, sigma 1 is acting on this plane. So, AB and CD, okay, these two planes, horizontal planes under, I mean these two planes experiencing the major principal stress sigma 1 prime. So, obviously the plane which is making 90° angle with the major principal plane, because so therefore, AB and CD become major principal plane, am I right. So, on AB plane your major principal stress is acting. So, therefore, this plane is happening as major principal plane. Similarly, BC and AD along this plane, basically you are your minor principal stress is acting, that is sigma 3 prime. So, therefore, these planes will become minor principal planes, right. So, now under this situation, that means the soil element is experiencing major principal stress and minor principal stress on these planes, and we would like to plot this thing in the Moore Coulomb the failure criteria. We would like to accommodate this thing in the Moore Coulomb failure criteria. Now, so sigma 1 is your major principal stress. So, that is plotted here. So, that means along this plane, why it is major principal stress? I mean this is the principal stress or principal plane, because on this plane there is no shear stress. So, therefore, this plane has to be the principal plane. So, therefore, this sigma 1, that is point B is shown here, right. Similarly, this point say E, okay. So, this point is basically the minor principal stress, because again this plane is a minor principal plane, and that plane basically will be considered as the minor principal plane, and along on that plane basically your minor principal stress is acting. So, that is nothing but sigma 3, right. So, from your basic say Moore circle representation or the concept, you are getting these 2 points sigma 1 and sigma 3, right, and then you draw the Moore circle, and then you tell, and then you get the Moore Coulomb failure criteria, which will be plotted on the same plot. So, that is given by this line F, G, D, H, say. So, this is my linear failure envelope, and this is touching the Moore circle. Now, you see here what is your maximum normal stress? This is nothing but the major principal stress, that is your maximum normal stress. Are you getting the failure there? No, right. Now, what is your maximum shear stress? Your maximum shear stress is lying somewhere here, that is the radius of the circle. Are you getting the failure there? No. So, that means the maximum shear stress or the maximum normal stress, they are not saying anything about the failure, whereas you are getting the failure somewhere else. Where you are getting the failure? When the Moore circle is touching the failure envelope at say point D, Okay. So, failure envelope is tangential at that point, tangential to the Mohr circle at that point D, and that point is basically telling about the failure, right. So, well, so I will stop here today. In the next lecture, we will continue this thing in with further details. Thank you very much.